This is an introduction to experiment 7b, calorimetry, Hess's law. So let's talk first about what Hess's law is and how we're going to make use of that. So Hess's law says that if a reaction can be expressed as a series of individual steps, then the total enthalpy change for the reaction will be equal to the sum of the enthalpy changes for each step. So what does that mean? Well, let's take a little space down here and draw some stairs. So if we're trying to get to the top of this, I don't know, maybe it's a podium or something. And if we go up one side, there's this kind of big step and then a small step when we get to the top. If we come up the other side, there's a small step and then a big step. Well, the distance or the height above the ground that we end up at is the same, regardless of which side we came up. So here we have step A and step B, and over here let's call this X and Y. So A plus B is equal to C, and X plus Y is also equal to C. If you're starting down here and you go up here, the distance or the height of that you've moved is the same whether you come from this side or from that side. A plus B equals C, X plus Y also equals C. The elevation here is a state function, meaning that it doesn't matter how you got there. All that matters is where you started and where you end up. Enthalpy is a state function. And so what Hess's law is saying is that if we can express that reaction as a series of steps, then the total enthalpy change for the reaction will be the sum of the series of steps. So this is the overall reaction we're going to look at. Copper sulfate reacting with ammonia, and these are the products. Well, we can express that reaction in two steps, step 1 and step 2. If we add these two chemical equations together, we get the complete reaction. So instead of just believing that, let's prove it to ourselves. So if I add these two reactions together, what I'm going to look for is anything that gets created on one side and destroyed on the other. So here I've got this funky looking ion, and I've got the same thing over there. So that's an intermediate, and we can cross those out. The other thing that's an intermediate is the water. So here in this step we had copper sulfate dissolving in water, and over here the result of this releases water, and so we can cancel those out. Then if we add what's left, we get CuSO4 solid plus 4NH3 aqueous to form this complex ion that you'll learn about in Chem 1B plus sulfate ion. So we can measure the enthalpy change for the step 1 reaction and for the step 2 reaction. And we can also measure it for the overall reaction. So I'm going to call this one delta H complete. And this is delta H for step 1 reaction. And this is delta H for the step 2 reaction. And so what Hess's law tells us is that delta H for step 1 plus delta H for step 2 is going to equal delta H for the complete reaction. Now, this is, of course, an actual experiment done with some rather simple supplies, and so it's not going to come out perfect. So what we're going to do is we're going to look at the percent error here. If we're super careful and Hess's law is true, then this will also be true. So we're going to look at how far off are we, and we're going to consider this part, the sum of the steps, to be the experimental value, and the delta H for the complete reaction, we're going to call that the theoretical value. And we're going to use our standard percent error, where we take the experimental value minus the theoretical value, divided by the theoretical value, times 100. And so what we're hoping for here is a 0% error or a very, very small error. And that would tell us that the experiment was successful, that we measured things carefully, and that Hess's law is true. So that's Hess's law. Now, how are we going to actually measure the enthalpy changes for these different chemical reactions? Well, that's another question. Let's get rid of some of this that I scribbled around in. We're going to use something called calorimetry, which literally means measuring calories. So calorie is an energy unit. Joule is another energy unit. And in calorimetry, we're measuring the energy that's transferred during a process. So here's the definition here. It's a technique used to measure the energy transferred during the process. That energy is called heat. We can't measure the heat directly, but we can measure the temperature changes that result from the heat transfer. So we're going to make use of this equation, Q equals mc delta T. Q is the heat. Here we're going to measure it in joules. M is the mass of the substance. C is the specific heat capacity of the substance. And delta T is the change in temperature. Now, it's important to remember that the change in temperature is defined as the final temperature minus the initial temperature. So the change in temperature is sometimes positive if the thing got warmer, or sometimes it's negative if the object cooled down. So we are going to be looking at the energy released by this chemical reaction. The reaction occurs within a solution, in the liquid. And so we're going to put the liquid in a calorimeter. In this case, it's a very simple one. It's just 2 styrofoam coffee cups. And we're going to see the solution is going to absorb the energy that's given off by the chemical reaction. So let me draw another bad picture for you. So here we have our solution. And this is the calorimeter itself, the coffee cups. And then inside, we have the chemical reaction happening. So if the chemical reaction gives off energy, releases energy, that energy is going to be absorbed by the solution and a little bit by the calorimeter itself. So the first law of thermodynamics, the law of conservation of energy, tells us that energy can't be created or destroyed. So if the chemical reaction loses energy, all of that energy has to go somewhere. It's going to go into the solution and the calorimeter, and we can measure the temperature changes of those and figure out what the energy loss from the chemical reaction is. And so that's what we're looking at down here. So we have Q for the reaction. That's what we're interested in. Q solution, we're going to measure by using the temperature change and its mass and its specific heat capacity. And Q calorimeter is the heat absorbed by the calorimeter itself, because it's not perfect. And we'll talk about how we're going to calculate that in a minute. But the first law of thermodynamics says that the sum of all of these energy changes has to be 0. So some of these will be positive and some will be negative, but they will all add up to 0. And so the math here is so simple that it becomes difficult because you overthink it. If we want to solve for Q reaction, I'm just going to rearrange this equation. Q reaction is going to equal 0 minus Q solution minus Q calorimeter. Or we could express that a different way and say it's negative Q solution plus Q cal. There's different ways of thinking about it, all comes out to be the same. The energy lost by the solution, the energy gained by the solution and the calorimeter is equal to the energy given off by the reaction, but it's opposite in sign. Okay, so what about that Q-cal thing? So the heat capacitor of the calorimeter. This calorimeter is a real object and it will absorb a small amount of heat. And so to get a better result, we're going to have to take this into account. So how do we measure that? Well, we're going to do that with a little pre-experiment. We're going to mix hot water and cold water in the calorimeter. And we're going to see how much of the hot water energy loss got transferred to the cold water and how much seemed to go away, disappear. That's what's going to the calorimeter. So here we can calculate Q for the hot water and the cold water based on their temperature changes. So Q for the cold water is the mass of the cold water times the specific heat capacity of the cold water, which being water is 4.184 joules per gram degree Celsius, times the temperature change for the cold water. That's going to be a positive number because the cold water is warming up. Similarly, we've got the hot water. That's the mass of the hot water times the specific heat capacity of water times the change in temperature for the hot water. Well, the hot water started hot and got cooler, so it is going to have a negative temperature change. So this one's positive and this one's negative. And if the calorimeter was perfect, then Q hot would be equal to negative Q cold. But they're not going to be exactly the same due to this Q cal. So here we can calculate what Q cal, the heat absorbed by the calorimeter, is. And again, this is very simple math. I'm just taking this equation here and solving for Q cal. And then a lot of people would prefer to look at it this way. We take the cold water Q and the hot water Q, we add them together, and we change the sign. And that should equal Q cal. So we can calculate Q cal in this way, and then we need to have a heat capacity so that we can correct for the calorimeter in our other relationships, in our other experiments. And so we're going to use this equation here. Q cal is C, where this C is the heat capacity, not the specific heat capacity, but the heat capacity. And we're going to use heat capacity here because the mass of the calorimeter is not going to change during the experiment. And so really what the C is, it's the specific heat capacity of the calorimeter times the mass of the calorimeter. So to calculate the heat capacity of the calorimeter, we are going to determine Q cal this way. So we know Q cal, and we know the delta T, and so we're going to rearrange this, and the heat capacity for the calorimeter equals Q cal divided by the change in temperature. So we'll do that experiment with the water 2 times, and find C for both trials, and then use the average.